Okay, the next topic in terms of SN1 reaction are what are called carbocation rearrangements, which are a little bit of a potential complication to writing the products of SN1 reactions, but we'll take these as Top Hat includes them at this point in the semester. So first of all, let me just give you an example here of a reaction, and then we'll talk about what a carbocation rearrangement is. And so let's say, for the sake of argument, that I reacted this molecule, and we'll put a chlorine here, and we will react this with water. Now, later in this lecture video, we're going to talk about how to determine what the mechanism of this reaction is, but we can start that conversation now. So first of all, I know this is a secondary alkyl halide, so it could undergo either SN1 or SN2. With water being a weak nucleophile from our discussion in the last lecture video, remember that weak nucleophiles can only react with carbocations. Can this secondary halide form a carbocation? Yes, and so that means the mechanism for this must be SN1, because weak nucleophiles can only react in SN1 reactions with carbocations, and this alkyl halide can react to form a carbocation. But if we actually did this reaction, we would see a little bit of this product being formed. So that's not a product that we would expect. We would expect the product to just simply be replacing the Cl with the OH after the water attacks the carbocation and loses an H+. But we would actually see some of this product formed. And so the question is, where does this product come from? Number one, it's a rearrangement because the OH is not attached to the carbon that was originally attached to the leaving group. It's attached to a carbon next to that. So let's first write the mechanism for forming the product that we expect, and then we'll talk about how we get the mechanism for forming the product that we would not expect. So I'm going to take my secondary alkyl halide and I'm going to break the carbon-chlorine bond. That means that I'm going to end up with a partial bond in the transition state, delta positive on the carbon, delta negative on the chlorine, as that is the way that the chlorine's becoming negative, the carbon's becoming positive, and that will give me then my carbocation intermediate. Okay. And then my water, as the neutral nucleophile, remember the whole water molecule adds to the carbocation, so it takes its lone pair and it's going to donate it to that carbon. And I'm going to write this all as one complete mechanism instead of in steps. So what would the transition state for that part look like? It would be a dotted line to the oxygen, because that's the bond that's being formed. If you don't want to write your charges in right now, then let's go ahead and write the product, and then we'll go ahead and go back and average out the charges. So in this case, the oxygen is going to have a lone pair and a positive charge. And so it's going to be that oxonium ion. Now if we go back and add the charges into the transition state, we have carbon going from +1 to 0, which means it has a delta positive charge as an average. Oxygen's going from 0 to +1. It gets a delta plus as well. So that's the transition state for adding the water. And then in the final step of this mechanism, we're going to take the water and we're going to have it catch the H+ as it comes off. So this pair of electrons will be used to catch that H+, and then when the OH bond breaks, the pair of electrons goes to the oxygen. We'll go ahead and hold off on the transition state and write the final product, and then we'll average out the bonds and charges. So we're going to end up with an OH, and then we're going to end up with now an H3O plus our hydronium ion, because that's what collects the H+. So in terms of the transition state then, we need to draw the bonds that are being broken, which in this case is the OH bond, and the bond that's being formed to the water. Okay, that's going to be the transition state. The charges, the oxygen's going from positive to 0, so there's a delta positive here, and then the oxygen on the water that's collecting the H+ is going to get its delta plus as well. So that would be the mechanism for the formation of what we would call the expected product here. And unless we actually do this reaction, we wouldn't necessarily know that the unexpected product is formed. And one of my issues with textbooks is that they start throwing around carbocation rearrangements, and some people, usually the people that write the problems are different than the people who write the textbook. And so the people that write the problems are just willy-nilly kind of making carbocation rearrangements happen, and there's no real systematic indication of when to rearrange and when not to rearrange. So one of the things that I do is I will tell you when to rearrange the carbocation. But there are some fundamental rules that we'll talk about in a minute. Okay, so this is the mechanism for forming the expected product. Now let's talk about the mechanism to form the unexpected product. Okay, and to form the unexpected product, I'm going to start by forming the carbocation. Since this is a secondary system, I'm going to go ahead and do the same first step. I'm going to lose the chlorine. I'm going to break the carbon-chlorine bond. I'm going to have my partial carbon-chlorine bond being formed. Carbon's going to be delta minus. Carbon's going to be delta plus in the transition state. And then we're going to end up with the carbocation. And a carbocation rearrangement is exactly what it says. The carbocation is going to move. Now, the rules are that the carbocation can only move one position. So the carbocation could either move here or it could move here. And you might say, well, how does that happen? And here's how that happens. How that happens is that a hydrogen that is on the carbon next to the carbocation is actually going to slide over. And it's going to slide over by taking both of these electrons and basically moving both of those electrons to now form the bond to this carbon. And so in this case, if that happens, the transition state would look like this. And this is a transition state. So what would happen is we would have, and well, let's write the final product and then we'll write the transition state. So the final product, if this hydrogen slides over, is to put the hydrogen here. But then this carbon right here lost the hydrogen, and so now it becomes positive formal charge. So this is actually what is called a 1,2 hydride shift. And it's a hydride shift because the hydrogen is basically moving with a pair of electrons, which means it's moving as a quote-unquote H minus, which is a hydride. So you can only move a hydrogen one position. So this 1 and 2 are relative numbering schemes. Okay. So in this case, that's what would happen. Now the transition state is going to have the hydrogen partially bonded to each one of those two carbons. And then the positive charge, if we average out the charges here in this transition state, this is the bond that's being broken, this is the bond that's being formed. So now in terms of the charges, this carbon positive, 0, there's a delta plus here. On this carbon, it goes from 0 to plus 1. There's a delta positive charge on this carbon. So this is the transition state for the hydride shift. And in this case, then, we're now going to form a tertiary carbocation. So rule number 1 is that you can only, if you do a carbocation shift, you can only move a hydrogen one position. You can only do a 1,2 hydride shift. Rule number 2 about carbocation rearrangements is that you must form a more stable carbocation. You have to form a more stable carbocation as a result of the shift. An equally stable carbocation or a less stable carbocation is not going to happen. Simply because this takes energy. This is a transition state. You need to get that energy back by forming a more stable carbocation. So for instance, if we said, well, okay, let's do the same thing over here. Let's take this hydrogen and let's do a 1,2 hydride shift here. What would happen is this pair of electrons would move and the hydrogen would shift over here. The transition state then would have the hydrogen partially bonded to this carbon and partially bonded to that carbon, with the delta positive charge moving from this carbon to this carbon. So that would be the transition state of that hydride shift, and in the end, what would we end up with? We would end up with the hydrogen shifting there and the plus charge shifting here. And so the problem here is this is a secondary carbocation and it's of equal stability. So I didn't pay for the transition state to get there. And so this will not happen. You will only get a hydride shift, you will only get a carbocation rearrangement when you form a more stable carbocation. So equal stability, it's not going to happen. So in this case, this carbocation is going to shift from the secondary position to the tertiary position. Now the water will come in and add to the carbocation. So that we're going to end up with the oxonium ion formed. The transition state for that, again, would be I'm going to form a partial bond here between the oxygen and the carbon, having a delta plus on oxygen, delta plus on carbon. So that is my transition state. And then in the final step, the solvent water molecule is going to come in and catch the H plus as the OH bond breaks and goes to that oxygen. And I'm going to run out of space here. So that I'm going to end up with a partial bond to that hydrogen, a partial bond to that oxygen. And a delta positive charge on the oxygen, a delta positive charge on the other oxygen of the water, that transition state, and then the final product would be that plus the H3O plus the hydronium ion. So that's how we form the rearranged product, is by that rearrangement mechanism. So again, the two things we have to, well, there's three things. Number one, I will tell you when to rearrange. Number two, you can only move a hydrogen one position. You can only do a 1-2 shift. And number three in this case, or number two in terms of the rule, you have to form a more stable carbocation. If you don't, then you're not going to do a shift. You're not going to do a carbocation rearrangement. Okay. Now, in terms of hydride shifts, you could also end up with another type of rearrangement, and that is you could end up with you can also end up with having a methyl shift and also a what happens if there's a primary system. So let's talk about that as well. So let me show you a similar reaction, and that is, let me put a methyl group here, let me put my chlorine here, and let me again react this with water. The rearranged product for this reaction would look like this. And in this case, this methyl group is going to do a 1-2 methyl shift. So it's possible to not only rearrange or to shift hydrogens, it's also possible to shift methyl groups. So in this case, if I asked you to write the mechanism for this reaction, the way we would write this would be to do now a 1-2 methyl shift. And so what we would do is we would write basically the same mechanism as we did before, only shifting the methyl group. So we would break the carbon-chlorine bond. And in our transition state, we would have the carbon becoming positive, delta positive, and the chlorine becoming delta negative, so that we could form the carbocation, the secondary carbocation in this case. And now if we're going to do a shift, we basically would say, well, we're not going to shift this hydrogen because then that would form another secondary carbocation that doesn't get us any extra stability. Now what I'm going to do is, and I should put my Cl- over here, so now I'm going to basically shift this methyl group over here, and so the methyl group is going to take its pair of electrons and now bond to that carbon. So in terms of the transition state for that, what I'm going to have is the methyl group is going to be partially bonded to that carbon, partially bonded to this carbon. Those two carbons are going to be transferring the positive charge from this carbon to the new carbocation, and the methyl group is going to be bridged in between them in this transition state to then form the more stable tertiary carbocation. So this would be our 1-2 methyl shift in the transition state. And then the water would come in again and would add to the carbocation. So in that transition state, we would end up with a partial bond between the oxygen and the carbon. This carbon would be delta positive. This oxygen would be delta positive because that's going to be the average of now forming the oxonium ion as the product as the water adds to the carbocation. And if I haven't mentioned it, when the oxygen has a positive charge, that's called an oxonium ion. So then in the final step, the water molecule would come in and collect this hydrogen as the OH bond breaks. So our transition state again would have partial bond to the hydrogen, partial bond to the water. Delta positive on this oxygen, the positive charge is being transferred to that oxygen of what will become a hydronium ion. And then the final product would be the rearranged with the OH in the tertiary position, the methyl group now shifted, and then it would end up with, you would end up with H3O plus as the water collects the H plus as it comes off in breaking the OH bond. So you can also end up with 1,2 methyl shifts if you can form a more stable carbocation from doing the 1,2 methyl shift. Okay. Now, in both of these cases, we started with a secondary system, and when you start with a secondary system, you will lose the chlorine to form the carbocation. But you can also get methyl shifts or hydride shifts from a primary carbon, but in that case the problem is that you can't form the primary carbocation. So how would a primary system shift? And let me show you an example of a system that we used when I was teaching at OU. So what we did was we took basically this system, and let's say we're going to go ahead and react this with water, and I'm going to go ahead and add some heat to this to make the reaction go. Now the product that I'm going to get is going to have this 2 CH3s attached to the carbon, but then the OH group is going to end up on the tertiary carbon, and I'm going to end up with a hydride shift with this hydride moving over to the carbon that was attached to the chlorine, was attached to the leaving group. So this would be the rearranged product. But the problem is I have a primary carbon that cannot form a primary carbocation. So this shift, this 1,2 hydride shift in this case, would have to occur in one step. So let me show you how that movement of the electrons in the atoms works if you have a primary system. So in this case, what would happen is the hydride would shift over to the carbon and the chlorine would leave all in one step. So the H is taking its pair of electrons, bonding to the carbon, and then the leaving group is leaving. Why? Because I can't lose the chlorine and form a primary carbocation. So this is going to be a concerted, meaning one-step mechanism. And the final product then of this step will have the positive charge on the tertiary carbon and the hydrogen now shifted over to the primary carbon, and then we would have a Cl- as the leaving group. So what's the transition state for this look like? Well, what bond am I forming, what bond am I breaking, and in this case, what bonds am I forming and what bonds am I breaking. I'm breaking a carbon-chlorine bond. I am breaking this carbon-hydrogen bond, but yet I am forming that hydrogen-carbon bond. So that would be the dotted lines, the partial bonds in the transition state. Now in terms of charges, there are no charges over here. There is a positive charge on the tertiary carbon, so this carbon would be getting the positive charge, and this chlorine would be getting the delta minus charge, since it's ultimately going to become a Cl minus. So you can end up bridging the hydrogen between the two carbons in the 1,2 hydride shift, kicking off the chlorine, and then rearranging this so that then the water would come in and attack this tertiary carbocation to form the product. We ran into this by accident when I taught at OU. I was teaching lab, and what we had was I had accidentally grabbed a bottle of isobutyl chloride, and I wanted to grab tertiary chloride. And we'll learn about this reaction second semester, but we were reacting this with iron trichloride, and what happens is that the iron, basically, the chlorine will break, and the iron kind of grabs the chlorine and pulls it off. And our ultimate goal here was to form the tertiary butyl carbocation that then we were going to do a Friedel-Crafts alkylation reaction with, and we were going to add the tertiary butyl carbocation to a benzene ring, which is a reaction we'll learn about second semester. But about halfway through the lab, one of the students came up to me and said, "Hey, we're using isobutyl chloride and not tertiary chloride." And then I went, oh, I must have grabbed the wrong bottle. But then I said, well, you know what? It doesn't matter. It's going to form a tertiary butyl carbocation anyway, so we'll get the same product. And then they wanted to argue with me about that, and I said, okay, fine. We'll make that a post-lab question. Show me how you get from the isobutyl chloride to the tertiary chloride. And that's exactly how it would happen. The hydrogen would shift, the chlorine would leave, being grabbed by the iron. So again, we would end up with the same type of transition state where the hydrogen would be moving, and a delta positive charge there, and a delta negative charge on the chlorine. And if you wanted to, you could write in the FeCl3, because ultimately over here we end up with FeCl4 minus. But we'll learn about that next semester. So actually I know this one occurs simply because we ended up with the correct product in this case. So this is how we handle a hydride shift, or even you could do the same thing with a 1,2 methyl shift. You could do the methyl shift as well, but when you have a primary system, you have to shift and lose the leaving group all at the same time, because you cannot form a primary carbocation. Okay, so that's all of the different ways that we can end up with carbocation rearrangements. And this will complicate SN1 reactions, but it's not really going to complicate it, because I will tell you when to do the shift. And I will also ask you in the mechanism, either I'll say, write the rearranged product, or I'll give you the rearranged product so that you have to recognize that you need to do a 1,2 hydride or a 1,2 methyl shift in those mechanisms. Okay, so that's carbocation rearrangements, and we will talk about those in more depth in the future. So now let's talk about SN1 versus SN2 reactions and kind of bring everything together. And what we'd like to be able to do is to predict, when will a reaction be SN1, when will a reaction be SN2. So what I like to do is I like to say, okay, let's create this chart of alkyl halide. Primary, secondary, and tertiary. And over here, let's talk about what happens when I have a strong nucleophile. And remember, a strong nucleophile has a negative charge. But what happens if it's a weak nucleophile? And remember, a weak nucleophile is neutral. And our two weak nucleophiles at this point are water and alcohol. So we can create this chart, and we could go ahead and fill it in about whether the reaction will be SN1 or whether it'll be SN2. So let's start with the primary system. What kinds of reactions can the primary system undergo? It can only undergo SN2. So the real question with the primary system is, will it undergo SN2 or will it not? So primary alkyl halide plus strong nucleophile is going to be SN2. What about a primary halide with a weak nucleophile? What did I say about weak nucleophiles just a few minutes ago? Weak nucleophiles can only undergo what kind of reaction? If you said SN1, you're correct. So a weak nucleophile can only react with something that forms a carbocation. Can a primary system form a carbocation? Oh, absolutely not. So what happens? We get no reaction. So primary plus a weak nucleophile is no reaction. How about secondaries? Well, let's go to tertiaries, because tertiaries are pretty clear cut. Tertiary can only undergo what kind of reaction? SN1. Can a weak nucleophile react with tertiary? Sure, because it can form a carbocation all day long. The secondaries are kind of in between. And this is where the gray area becomes, because if you have a secondary, then does it undergo SN2? Does it undergo SN1? Because it could do both. And this is where there's a lot of gray area. And if I incorporate a lot of gray area, the problem is that people get confused. I remember when I first started teaching at Kansas State, the person that was teaching the majors organic, because I taught the sort of dietitian vet school, one semester. It wasn't one semester, it was like 2 semesters, but it was really kind of a lower level. But we did do a lot of mechanisms in that class. I remember the guy who was teaching the majors class and pre-med class, and he's like, I don't even know if I believe what we're teaching about SN1 and SN2. And I said, well, maybe you're caught up in the gray area. Maybe you're focusing more on the exceptions than actually just dealing with the clear-cut examples and then including the exceptions sort of as we go along and get more comfortable with it. So I'm going to take my own advice, and that's what I'm going to do here. So we're going to make this fairly clean cut right now. And that is that a secondary halide and a strong nucleophile is going to do SN2. And it's actually not even that clean cut, because remember, weak nucleophiles can only react with, in what mechanism? SN1. Can a secondary alkyl halide form a carbocation? Yes. So when it's a strong nucleophile, secondaries will be SN2. When it's a weak nucleophile, they'll be SN1. So this is the chart that we have to remember in order to predict the reaction mechanism that the alkyl halide is going to undergo. And instead of just putting this chart up, and there's a more complicated chart in the textbook that we'll eventually add into, but in this case, this all makes sense, right? Tertiaries only do SN1. Primaries only do SN2. Neutral nucleophiles can only do SN1s with halides that can form stable carbocations. So right now this table kind of makes sense. It might be a little oversimplistic, but that's okay. We'll make it more complicated as we go along. Okay? So that's how we're going to predict the mechanism of the reactions. Now, let's take a little diversion here and talk about the stabilities of alkenes. And you might say, well, wait, why? Well, because SN1 is always accompanied by what is called an E1 reaction. And there's going to be an E1 and an E2 mechanism. E1 for unimolecular, E2 for bimolecular. But these are elimination reactions. And what does elimination reaction mean? It means that what I'm going to do is I'm going to take an alkyl halide to start with, and I'm going to eliminate HX from that molecule and form a carbon-carbon double bond. And the major product of this reaction in terms of E2 is going to be the most stable of the not of the carbocations, but of the alkene. So we need our rules about what is the more stable alkene. And so the first thing we need to know about alkenes is that if you're going to make them stable, you can make them more stable by pushing electron density into them. Okay, so if I can push, the more electron density I can push into a double bond, the more stable it will become. Well, if you're having a sense of deja vu, like, wait, didn't we do that with carbocations? We did. So let's do the same thing here. Let's add an alkyl group to our alkene. And when we do that, remember the hydrogens are all delta plus, and the carbon's delta minus. How did it get delta minus? Because it's slightly more electronegative than the hydrogen. So now this delta minus is going to push electron density into the double bond. And the double bond likes that and becomes more stable. So what would be the most stable alkene? Well, alkenes can only have 4 things attached to them. So the most stable alkene would be having 4 alkyl groups attached to the double bond. That would be the most stable alkene. Well, 4 most stable, 3 next most stable, 2 next most stable, 1 it's stable, but in terms of ranking, the more stable alkene comes from the more substituted alkene. So now all we have to do is just be able to count the number of alkyl groups that are attached to a double bond. All right, so let's do a little review here. Let's do a little game. How many alkyl groups are attached to this double bond? Give me a number from 1 to 4. Okay, did you input your number? A couple ways to do this problem. One of the ways to do this problem is to count up the number of alkyl groups or count up the number of hydrogens and subtract from 4. Here's an alkyl group. Here's an alkyl group, so there's 2 here. Most people can handle the acyclic double bonds with no problems. It's the rings that sometimes cause people problems when they first start. So, how many alkyl groups are attached to this double bond in the ring? Give me a number from 1 to 4. Okay. The first thing I would do is I would put a hydrogen here. I would draw in my hydrogen. How many hydrogens are there in this double bond? There's 1. So that means the other 3 groups must be alkyl groups. So there's a grand total of 3 alkyl groups attached to this double bond. Now you might say, okay, carbon, over here's a carbon, and over here's a carbon. So those are my 3 alkyl groups. Now the stability of a double bond does not depend on the type of alkyl group. It only depends on the number of alkyl groups. So a methyl group, an ethyl group, a 100 carbon chain are all treated equally. So it's the number of alkyl groups, not the type of alkyl group, that leads to the stability of an alkene. Okay? So that's how we judge the stability of an alkene. More substituted, more stable. Why? Because the alkyl groups push electron density into the double bond, and that makes the double bond more stable. So if you're kind of looking at, oh, that's like we did with carbocations, exactly. This is a general theme. Things that like to get electron density love to have alkyl groups attached to them. That makes them more stable. Okay. Now, why do we need to talk about the stabilities of alkenes? Because now what we're going to do is talk about E1 reactions. So an E1 reaction is an elimination reaction. So it's going to form a double bond. So let me take something fairly straightforward, like this molecule, and say that we are going to do an E1 mechanism for this. And so the first step in this mechanism is going to be to break the carbon-chlorine bond. I'm going to write the hydrogens on the carbons next to the chlorine, and I'm going to define those here in a minute. So I'm breaking the carbon-chlorine bond. That means in the transition state a delta plus and a delta minus in the transition state to then give me the carbocation. And this is a secondary carbocation, so I'm perfectly legitimate in writing it. And then there would be a Cl minus up here. Now, have we done that before? Yes, because this is the same step as an SN1 reaction, which is the problem with E1. Whenever you do an SN1 reaction, you always have the potential of getting E1 products. So now what can happen is, let's say there's not another nucleophile in the mixture that's going to come in and add to the carbocation. Or maybe the nucleophile is a little bit late in adding to the carbocation. Or, better yet, let's say that I add heat to this reaction and force this elimination to occur. Now, what can happen is that I can lose either one of these 2 hydrogens to form the double bond. Now, in this case, I'm going to do something that I've been chastised at the awesome Kent State University for doing, which is why part of the reason why they're not accepting organic at John Carroll to be the same as their esteemed organic chemistry at the Kent State University. And that is that there's what is going to grab this hydrogen. And basically, let's say that chlorine now grabs this hydrogen. You could say, why doesn't the chlorine come in and add to the H+? Well, if it does, then this whole system goes backwards. But let's say the chlorine doesn't add to the carbocation. Let's say it kind of is going to catch this H+ as it leaves. So if I break this carbon-hydrogen bond and I take the pair of electrons and give it to this carbon, then I'll form a double bond. And then the chlorine's going to kind of just catch the hydrogen as it comes off. So what is that going to look like in terms of a transition state? I'm going to break the carbon-hydrogen bond. I'm going to form a carbon-chlorine bond. I'm going to form a double bond. And so I'm going to form this double bond between that carbon between the two middle carbons. And I'm going to form HCl. Not because the chlorine is taking an active role in ripping this hydrogen off, but just because that H plus is going to leave and the chlorine is going to catch it, just like we did with water. And I'm trying to adjust that so that, I'm teaching organic in the proper way. But I don't want to leave the misconception that the chlorine is, coming in here and aggressively taking that H plus. It's not. It's just catching it. So I can form this double bond. Now, in terms of charges, the chlorine would be delta minus. This carbon would be delta positive, and there's no other charges here. So this would be the transition state for losing this H as an H plus and then forming the double bond. So if I have, let's say, carbon, if I labeled this carbon A and carbon B, and I lose HA, the hydrogen attached to carbon A, I would get, let's say, product A. And let's say I did the same thing with B. So I'm just going to do that over here because I need more space. So let's say that I could lose, you could say, why do you lose HA? Couldn't you lose HB? Absolutely. So I could take this HB on the B carbon here, and I could take this pair of electrons, use it to form the double bond, and then have the chlorine catch the H plus as it comes off. And so that would lead to the same type of transition state. I'm going to combine this H and just make this a CH2. I'm going to partially form the double bond. I'm partially breaking the carbon-hydrogen bond. I'm partially forming the chlorine hydrogen as the chlorine catches it. For that transition state then, we have a delta positive charge on that carbon and a delta negative charge on this chlorine. So then that final product would have the double bond now attached to the end carbon. And I would still end up with HCl, and I'm going to call that product B. Okay, so whenever you do an elimination reaction, in this case an E1 mechanism, the E1 mechanism, you basically are going to form possible products by losing the hydrogen attached to the carbon, attached to the carbon, attached to the leaving group. And so you have to identify those two carbons and those two hydrogens to know what the two potential products of the reaction are. And I get tired of saying the hydrogen attached to the carbon attached to the carbon attached to the leaving group, hydrogen attached to carbon attached to carbon attached to the leaving group. And so there's terminology that we use here, and I might as well introduce that terminology, which is the carbon attached to the leaving group is called the alpha carbon, and the carbons attached to the alpha carbon are called the beta carbons. And then carbons attached to the beta carbons would be the gamma carbons on down the line. Hydrogens attached to the beta carbon are beta hydrogens. And so in an E1 process, you're going to lose a beta hydrogen. And so the possible products that you form are going to come from losing the beta hydrogens and the leaving group. And so you end up forming, in this case, two possible products with the double bond in these two different positions. Okay? So we'll talk about in a moment just writing the product without the mechanism. In writing the product without the mechanism, you identify the alpha carbon, and then you identify each one of the beta carbons. Okay? So this is the mechanism for E1. Why is this E1? Why is this unimolecular? Because the rate determining step of this reaction is the formation of the carbocations. that is the rate determining step. And so it's just like SN1. It's a unimolecular reaction. Now in the future, I'm going to redefine my E1 and E2 or SN1 or SN2 and basically say all unimolecular reactions undergo carbocation intermediates. They have carbocation intermediates. And all two mechanisms do not. So it's a much more broad definition of 1 and 2. But in this case, E1 accompanies SN1, and we'll talk about that more in the future. Okay? So then the question is, I now have two products. This is the first time I've had two products, and now I have to talk about what is the major product of this reaction. And the major product is the product in general that has the highest percentage. So if there's just two products, whichever one has the highest percentage is the major product. In predicting the major product, there are always rules. And so the rule for the E1 reaction is that the major product of an E1 reaction is the most stable alkene. And then you're going, hey, that's why you talked about the most stable alkene, the rules for that, in the last slide. Yes, I am a trained professional, and so that's why we talked about most stable alkene to begin with. So now this is then how we predict the major product. So now my question to you is, which product, A or B, is the more stable alkene? And remember, more stable alkene means more substituted. So which is the more substituted, which is the more stable alkene? What's going to be the major product of this reaction? A, B, or if they had the same number of alkyl groups attached, it could be both. So is it going to be A, B, or both? Okay, how many alkyl groups are attached to this double bond? Well, there's 1, 2, 3 hydrogens, which means there's just one alkyl group. How about this double bond? How many alkyl groups? There's 2 hydrogens, which means there's 2 alkyl groups. Which one is the major product? A. A is the major product of this reaction because it is the more substituted, more stable alkene. Okay, so that's why we talked about that, is because now we have to apply that to E1 rules. Okay. Okay, so we will talk more about E1 mechanisms in the next lecture, but I think at this point you have the basics of E1, and we'll talk about more of this, and then we'll add in E2 in the next lecture video. So remember, this was the carbocation rearrangements and the E1 mechanism, and the most stable product for an E1 reaction is the most substituted, most stable alkene. Okay?